All right, in today's video, what we're going to talk about is equilibrium, and this is part one of a multi-part series on equilibrium. All these videos can be found on my YouTube channel. So the focus today is really to talk about setting up an equilibrium expression, kind of what situation gives rise to equilibrium, understanding the reaction quotient, and then just doing some conversions between an equilibrium constant in the concentration form and in the pressure form. So let's get started, and we're going to look at a reaction where basically dinitrogen tetraoxide just decomposes to two molecules of nitrogen dioxide. And the nice thing about that is that dinitrogen tetraoxide is fairly clear. So here's a picture of that in the bottle over here on your far left. And as it becomes nitrogen dioxide, it's actually a kind of a dark gas. So basically in a sealed container, you start off dinitrogen tetraoxide, and over time, there's a clock running on the top. It becomes more and more colored as NO2 starts to build up in there. And finally, there's some mixture of NO2 and some of the starting material. But under equilibrium conditions, at a set temperature, those concentrations become set under the conditions of this bottle. All right? So how do you write an equilibrium expression? How do you describe that mathematically? And really, we can go back to our kinetics, that basically what's going on the forward rate, the rate at which N2O4 is decomposing at equilibrium, becomes equal to the backwards rate of NO2 gas recombining, and this reaction running in reverse and going back to N2O4. So one of the assumptions here is that the forward reaction becomes equal to the rate of the reverse reaction under the conditions of that bottle, and at that point those are the set concentrations. So if I took it this way, I'd go back what I'd learned on earlier videos about kinetics, or the rate at which things happen. And if I was to express the forward rate, remember how we express rate expressions, we only deal with reactants. So basically we take K, which is the rate constant for the forward reaction, times the concentration of the reactants raised to the power, which in this case is 1. Going in reverse, you take the K, the rate constant for the reverse reaction, times if we were going in reverse now, this is the reactants over here, the NO2 is the reactants, raised to the second power. So we're saying these two are equal. So now if algebraically we rearrange that reaction and we put K forward divided by K reverse, you could equal the products squared over the reactants to the first power. And here is what we call the equilibrium expression, where basically you always put the products over the reactants, and that constant, now if you combine it together, you can just call it an equilibrium constant. And now notice here's the key, that's the difference between rate, which is small k. When you're talking about equilibrium, this is just about concentration, you're using the large K. This is a temperature-dependent equilibrium constant. This is now a new expression for the concentrations at any temperature without integrating. And if you want, you could rewrite it this way. Instead of putting these old kinetics constants in here, the rate constants, you can express it with this big K. And this is a generic form of any equilibrium expression. Now K will change as the temperature adjusts, and we know that in terms of rates forwards and backwards adjust, so you would assume that this K adjusts. But at new temperatures, then these will find new concentrations. So in general, for any reaction, if you want to write the equilibrium expression, so here we go, we're looking at reactants here. This is the A, this is the coefficient in front of the A. A is some reagent, B is some reagent, C is some product, and D is some product. The C and D are the stoichiometric coefficients. You can always write it, big K, and this is by concentration. Notice these brackets, I want to remind you, are molarity. Okay, so you go to the products, raise them to the power of whatever their coefficients are. divide that, so that's in the numerator. The denominator basically is the reactants raised to the power of whatever their coefficients are. So for a particular system, whatever A and B is and whatever the reaction is and the given temperature, the same equilibrium state is attained regardless of the starting concentration. So this is a real cool thing about how this works. So no matter what the starting concentrations is, they'll finally settle into equilibrium. You divide the products by reactants, you'll always get the same number at the same temperature. It's kind of a cool phenomenon. Although we derive this from kinetics, time, we've now left time and we're totally focusing on concentration. So from now on, whenever you see the big K, think, oh, these are for concentrations at equilibrium. We're no longer paying attention to the time it took to get there. That's the whole kinetics section. That's the small k and the rate expression. And once again, reminding you that anytime you see this bracket assumes molarity, it's the concentration, moles per liter. So there's your reminder about the equilibrium expression. Always put your products over your reactants. All right. So now let's just generally interpret an equilibrium constant, that K. I just want to introduce you to a phrase you'll hear a lot of the times. If you have reactants forming products and this reaction doesn't want to move towards products, in other words, it stays back at reactants, sometimes you'll hear that reaction described as to the left. This reaction stays to the left. On the other hand, if it goes like a shot and you end up with a lot of products, then a lot of times you'll hear that referred to as to the right. But there's numbers associated with the K, and basically they are, if the numbers are less than 0.1, for example, here's a reaction where nitrogen reacts with oxygen to form nitrogen monoxide. Now we know this reaction must not happen, right? Because this is stuff we breathe all the time. And it's obviously not forming this poisonous nitrogen monoxide gas. So this doesn't happen. It stays back at reactants. How do I know that? Look at the K and look that it's a very, very small number, much less than 1. Okay, so the minute you see a K with a number that's much less than 1, you assume it stays back at the reactants. The reaction's not very favorable. If you see a K that's somewhere in that regime from 1 to 10, okay, that's actually kind of in the middle. You're going to get half reactants, half products. It goes halfway. So, for example, this bromine monochloride will actually decompose into the bromine gas and chlorine gas. And the K for that is 50-50. It's basically just a rough way to interpret that number. And if it's strong to the right, then this number to the exponent is well above 10. And so this is carbon monoxide reacting with oxygen, and you're ending up with carbon dioxide. All right, so that's the first part, just kind of generally interpreting the K. The second part is just a few caveats about writing an equilibrium expression. So what we have going in here is we're basically taking calcium carbonate and it's decomposing into carbon dioxide and calcium oxide. So it's just decomposing. And as you let that reaction go, the pile of calcium carbonate starts to shrink and the pile of calcium oxide grows, and they'll reach some sort of equilibrium. But here's the key to this picture. We're basically saying, look, you know what? The concentration of calcium carbonate, there is no moles per volume, because no matter what concentration you're at in a solid, it's the same concentration of moles per volume. All right, even if you have this big pile, it has the same moles per volume as you do in this smaller pile. So really, solids do not change their concentrations in the middle of the reaction. Concentration is something that's used for gases or for solids dissolved in liquids, right? Aqueous solutions. So that's one thing. Okay, here's another thing to watch out for. So we look at this one. Here's potassium reacting with water. If you drop these two potassium chunks, so there's the solids again. So solids couldn't be part of an equilibrium expression. You drop them in water, you're going to start generating potassium hydroxide and hydrogen gas. So here they go. They start dropping. They start reacting inside this reaction or in the water. And as they do, they form hydrogen gas See it up here? And also, they make this aqueous potassium hydroxide. So, as these start to decompose, they form a little hydrogen and they form this aqueous solution. But if this is a sealed container, in theory, you might be able to stop this, although this equilibrium constant is very high, so it's very favorable to products. All right? So let's break that apart according to what we learned earlier in kind of figures. Solids do not change their concentration, so that cannot be part of the equilibrium expression. Liquids also don't change their concentration. The moles per liter are constant. Now, potassium hydroxide, on the other hand, is a true solution. It's changing concentration. The more this reaction runs, the more potassium hydroxide that's going to form. Gas, on the other hand, it also could change concentration. This is not always so obvious, but think of it this way. What if I was to change the volume of that container, right? Well, now all of a sudden the concentration of hydrogen has increased because I have the same moles but in less volume. So gas does have a concentration. So this is important when we go to do equilibrium constant expressions. So let's set up this equilibrium constant expression. Remember, products over reactants. So K equals, what are my products? Well, potassium hydroxide, that's legitimate because it is an aqueous solution, so I can express it. See that 2 out in front, the coefficient? That becomes a power. Hydrogen, oh, that's a gas. It also has a concentration, so I can put that in there. Now I go over here to reactants. That's what goes in the denominator. Well, it so happens that potassium's a solid, so it doesn't change concentration, so it does not go into the equilibrium expression. Water also is a pure liquid, does not have a concentration, does not go into the equilibrium expression. So in essence, this is the reaction. At equilibrium, at a set temperature, there will be an amount of potassium hydroxide and hydrogen multiplied together will give me some K. All right, so let's just do this part. Let's practice writing equilibrium expressions. So here's what you need to do. Once again, remember, gases, aqueous, they go into the expression. Solids and liquids do not. So with that in mind, you have 3 reactions up here. See if you can balance them first, because just for example, I can quickly glance here and see there's 2 nitrogens here, there's only 1 here. So these need to be balanced. So balance out these 3 reactions. Then see if you can write the equilibrium expression. K equals products over reactants. So stop your video, work out the answers on your own paper. When you're ready, restart the video and we can check your work. So let's see, how did you do? Here's question 1. Once you balance it out, it's all gases, so all these reactants and products will go into the equilibrium expression. NO2 is raised to the 4th power, O2 is raised to the 1st, N2O5 is to the 2nd. There's your equilibrium expression. Okay, second reaction, all balanced out. Gas, that'll go in the equation. Aqueous goes into the equation. Liquid does not. Solid does not. All right, so you write it with products over reactants, but in this case, both reactants don't go into an equilibrium expression. Sodium hydroxide is raised to the 2nd. Okay, so here you have propane, 3 carbons, burning with, this is a complete combustion reaction. So now we should know from experience that this should go, when you find the K, later on we'll talk about what this actual K is, you assume it's going to be very high because this reaction goes like a shot. It goes completely to products. But anyway, for right now, you go over here and you find they're all gases, so we can put them all in the expression. CO2 to the 3rd, water to the 4th. Go back to the reactants to the 1st, and then the oxygens to the 5th, and there you go. So as we know that if you remember back to Dalton's law of partial pressures, you remember that if you have all gaseous products and you start to do stoichiometry on them, you know that the the partial pressures of these three materials is exactly related to the molarity of these three materials. So in other words, the concentration and the partial pressure are both related. So consequently, a lot of times in an equilibrium expression, instead of setting things up in terms of concentration of something, you might set it up in terms of pressure. And in that case, you have a different equilibrium constant. It means the same thing, it's just that
when you see the subscripted letter
P, that means it's an equilibrium expression set up in terms of partial pressure. If you see the C, it's the equilibrium expression set up in terms of molarity concentration. Okay? But you can always convert between the two. They're related. So if I set it up by pressure, fairly straightforward. You go over here to products, just pressure raised to the second power, so it's the NO2 pressure, partial pressure, divided by the nitrogen monoxide partial pressure. That also has to be squared, times the oxygen partial pressure. That's to the first power. So there's an equilibrium expression set up with a gas pressure equilibrium constant. So here's the original one we learned, a concentration. And no surprise here, you basically products over reactants raised to their coefficients. So here's how you make the conversion. I'm going to just show you the quick version first, and then I'm going to show you how to do the derivative. So here's how you get from one part to the other. If you know the Kc, you take it times R, the gas constant, universal gas constant, times T, and you have to also raise it to the power of the change in moles of gas. So we're going to talk about this delta N real quick, what the heck that means. So R in this case is the universal gas constant, 0.0821, and the units on it are liters atmosphere per k-mole. And always remember temperature is in K when you're doing these kind of calculations.
In order to determine the delta N for the reaction, you count the moles of gas on the reactant side, and then you count the moles of gas on the product side.
And the change is what that delta N is. If it doesn't change at all, you call that 0, you raise that to the 0. Anything raised to the 0 is 1, so then Kp equals Kc in that conditions. But let's talk about this reaction real quick. What is the delta N? Okay, so there's 2 moles of nitrogen monoxide, 1 mole of oxygen, see there's one in front here, 2 moles of nitrogen dioxide. So the change went from 3 from reactants to 2, so the delta N is actually a -1 in this case. So in this case, the Kc, in order to get to the Kp, you take the Kc times RT raised to the -1, which means divide by RT, equals Kp. Okay, let me give you the derivative for this. Basically, it's based on the universal gas law. So PV equals nRT. P is pressure, V is volume in liters, N is moles, this is R, the R gas constant, T is in K. So now let's just do a really simple math move here, okay, just to see how we derive this thing. If I took pressure over RT equals N over V, right here, wouldn't this N over V, that's the number of moles by volume, isn't that concentration? Okay? So then couldn't you just multiply that out and say, oh, okay, the pressure of gas equals whatever the concentration is times RT. And that's exactly what happened over here. The Kp equals the K of concentration times RT. The only catch is you got to also raise it to the power of the number of moles that are changing. So if I was to work this little thing all the way through, here's how it would look. Let's just take an example. We take ammonia, NH3, we react it with oxygen, we make dinitrogen oxide and water. So if I set up this expression, we go, okay, there's 2 moles of this reacting with 2 moles of that. It forms 1 mole of that and 3 moles of that. So in this case, the delta N is it went from 4 moles of gas on this side to 4 on that the delta N is 0. But let's just work it out. Okay, so now I'm going to do this in terms of pressure. Here's the equilibrium constant pressure version. So pressure equals that. So now I'm going to do the substitution that we learned right here. Look, the dinitrogen oxide times RT. There's water to the third, RT to the third. See what I'm doing? I'm basically substituting this in everywhere that I see a concentration. And now all I need to do here is just isolate out the RTs. Let's get rid of some of the shrubbery, get rid of the concentrations and isolate the RTs, and look what happens. If I just got that single RT there, there's a cubed RT, there's a squared RT, there's a squared RT. Now let's just collect everything. Now do you see why the delta N comes into play? If it's the same on both the reactants here are the same as the products over here, then the RTs will actually cancel, and Kp equals Kc. All right, so now let's look at a separate situation. Now we're going to take ammonia, break it down into nitrogen and hydrogen. One source that's been proposed for carrying around hydrogen gas is carrying it in the form of ammonia and then using a catalyst to decompose it. But anyway, let's just get back to the chemistry at hand here. If I took the moles of ammonia here, it's 2. If you go to the product side, it's a total of 4. So the delta N here is 2. That's what we know. So let's see how we derive that. Same thing. Okay, remember this little shortcut we have here. Anytime you have the pressure in terms of the gas, you could express it concentration times RT. Would mean the same thing. So we set up our equilibrium expression with Kp, just like I've shown here. Products raised to the proper power of the coefficients. Now I'm going to make that substitution right there. Everywhere I see a PG, right? I'm going to make this substitution. But because it's powered, so this is to the first, right there. This is cubed, so all this is cubed. This is squared, so all this is squared. Now if I just isolate out the RT just so I can focus on it, I've got an RT times an RT cubed divided by RT squared. And voila, you get RT to the second power. And so in essence, that is what gives rise to this. Here's your shortcut. Anytime you have a Kc, take it times RT raised to the delta N, meaning how many moles is different products in comparison to the reactants. And that will give you your Kp. So there's one conversion. So now you practice. Here's calcium carbonate solids turning into calcium oxide and carbon dioxide. So why don't you do this? Here's the Kp. It's 2.1 times 10 to the minus 4 at 1000 K. Can you find the Kc? Stop your video. Try and set it up on paper. Make sure you think about the delta N going from here to here and see what you come up with. Okay, let's see how you did. So let's get down to the solution. The first thing is going from products, the number of gases are 1 mole. Reactants, there are no moles of gas, so 1 minus 0 is 1. So the delta N is for the gases is 1. So here's your original equation. Remember, you take Kc times RT raised to the power of delta N. In this case, it's 1. So I want to now solve for Kc. If I was to solve for it, I would divide through both sides by RT. And so you'd basically have Kc equals Kp divided by RT. That's another way of expressing divided by. So now you just plug in your numbers, solve, you get 2.6 times 10 to the minus 6. All right. So now we're going to introduce the idea of the reaction quotient. So if you take a general reaction, you can solve the reaction quotient by setting it up just like the equilibrium expression. So mathematically it looks the same. The only difference is what are you plugging in here. Q is the ratio of products to reactants at any point in a reaction. So now we're not talking about once it's settled into equilibrium. Remember the original reaction where we started off with a clear gas and we decomposed to a dark brown gas? This could be set up at the very beginning. What are the initial concentrations? And you plug them in. Okay? And obviously at equilibrium, then the QC becomes the K. All right? And this is going to make more sense as we go on, so we're just going to kind of get used to the format in this video. QP follows the same rule as K. In other words, if you wanted to express QC, which is the reaction quotient in terms of concentration, but you would rather express it in terms of gas pressure, you can do the same little conversion we just learned. Okay? So now let's go back to this original reaction. Very straightforward. But what if we entered the amounts of N2O4 and NO2 at this point along the journey? Okay? Or at this point, early on or later on. And obviously if you let it settle into equilibrium, then the QC equals the KC. The reaction quotient equals the equilibrium constant. Okay? But let's talk about, and that is, for example, this reaction, the K is actually 10.4. So it goes kind of half and half. That's kind of a way of describing that. It's not really high, so it's not strong to the right, but it's also not back at the left. That's how you can interpret that size of K. Q, on the other hand, sets up the exact same way. It's just at any time along the reaction. So now let's follow the reaction we were just looking at. And so we got 4 experiments, and this will be instructive. Remember, we're putting in dinitrogen tetraoxide, letting it decompose, it's becoming nitrogen dioxide. So initially, here's experiment 1. We basically add just pure N2O4. So it's 0.1 molar. Well, then if I plug that in, right, that would be 0.1 molar on the bottom, 0 on the top. That would end up being 0. So the Q at that point is 0. But if you let this reaction run over time, it's obviously going to decompose until where it's kind of some NO2 forms and some N2O4 forms. So if I take these concentrations at equilibrium and plug them right back in here, sure enough, they're going to equal 10.4. Now here's another scenario. What if we ran it backwards? What if we literally took an outside source of nitrogen dioxide? And so now I pump that into the bottle, seal it, so right at that moment, it's all NO2, nitrogen dioxide. But according to this equilibrium, it's going to settle into a concentration, right, over time. So once again, this Q then would put 0.1 on top divided by 0. So that's undefined when you divide by 0. So we're going to ignore that Q for right now. But you do know as you let the reaction just settle in, it's going to basically, this is going to run in reverse until it settles in. And sure enough, that 0.1 starts to lower and the N2O4 builds up until finally you get 10.4. Okay, here's the third expression. Now we're going to go in 50-50. I have a source of nitrogen dioxide. I have a source of dinitrogen tetroxide. I add those gases in equal proportions, both so they're 0.05 molar right at the beginning. So the Q at that point, if you took 0.05 and plugged it into this expression, you'd square it, divided by 0.05. Well, that would obviously cancel one of the 0.05s, and the Q at that moment is 0.05. But as you let the reaction go, that Q is going to start to lower, right? Or raise until finally it becomes K when it settles back down. And the final concentrations are going to still be 10.4. And here's the last reaction. Now we're going to run it high on the N2O4 side. A little bit NO2. The Q is actually 0.008 molar. You let the reaction run, and sure enough, it settles right back into about 10.4. Now, this is also kind of instructive. Remember, there's a little imprecision in this. Okay, this is just a true experimental data, so you should see a plus or minus here on the last digit if your precision is correct. So this holds. And it's kind of instructive. So here's where you're going to end the video. I want you just to practice the things we've learned today. If you have this equilibrium expression, or you have this equilibrium reaction, you set up your equilibrium expression, can you solve different parts? So question 1, Hey, what if you know the NO2 concentration, but you don't know this and you know all the other pieces? Can you solve for this? Here's the second question. Now I don't know the NO2, but I know the dinitrogen tetraoxide and the equilibrium constant. Can I solve for that? Third question. Hey, I know the Kc, right? These are in terms of concentration. Can I turn it into a Kp? That's the third question. And 4, so if you know the concentration of NO2 at 0.5 molar and you know the concentration of dinitrogen tetroxide at 0.5 molar, can you solve for the Kc? All right, so same thing. Stop your video. Try and solve the problems. When you're ready, we can restart the video and you're ready to check your answers. So let's see how you did on the first one. Basically, here's the unknown. We don't know the dinitrogen tetraoxide. So it's pretty much algebra. Bring this up to this side and divide through by 10 to the 4, and you basically, 0.5 squared divided by 10 to the 4, and you get 0.024 molar. Second question, similar thing, we just have a different variable missing. Multiply through by 0.25, then take the square root of both sides. NO2 concentration is 1.61 molar. Okay, if you know that this is 10.4, how do you get back to the Kp? Well, one of the keys is the delta N, right? 1 mole of gas on this side, 2 moles of gas on that side. 2 minus 1 should be a delta N of 1. Set that up. There it is. Temperature 473. 1 is the delta N. Here's the universal gas constant. Kc we know. It's right there. Right? Kc we know. Plug and chug. You get 403, and these are actually unitless dimensions often. So now this may have a dimension that falls out because the universal gas constant is liters atmosphere per kmol. Okay? 10 itself could be unitless. Okay? It's actually, if you go up here, you can plug in mole squared over mole, so that this actually has the K in this case has a molar ratio. But that, generally speaking, you think about these K as being unitless. Okay? So now, what is the Kc? If the NO2 is 0.5 molar and the N2O4 is 0.5 molar, you just plug and chug. There you go. The Kc is 0.5. Now remember, once again, this is a concentration, a QC. It really is meaningless unless you compare it to this. I know that 0.5 has to change to that in order to become, when it reaches equilibrium. And that's going to be the subject of the next video. So I hope this introduction has gotten you going on how to set up an equilibrium expression, how to correlate the magnitude of K with whether it's going to be far to the right, it's going to stay back at the reactants, far to the left. I hope that you can differentiate an equilibrium constant from a reaction quotient. And then the other thing is, can you convert between an equilibrium constant expressed as concentration and an equilibrium constant expressed as pressure?